All right, everyone. Welcome to today's webinar. We've got a really exciting topic for you presented by Galaxy Solutions. Expero and Tarleton are going to give you a really sort of detailed walk on improving and really sort of mitigating insurance losses. And we're going to walk through some really great case studies. Today's session is being recorded, so there will be a link for that, and we'll send that out after the webinar. If you have questions during the middle, go ahead and enter them in the response bar on the bottom, and then we'll leave some time at the end for live question and answer. So without further ado, we'll go ahead and get started. Got a great lineup for you. So Troy Thorne, Jesse Crawford from Tarleton. They're going to walk through sort of why Tarleton is such a different approach with Troy, and then Jesse and Graham are going to walk us through sort of the details of what is the magic, if you will, behind the scenes. And my name is Scott, and I'll be our tour guide today. I'm going to sort of set the stage for why this is such a difficult problem, and then give you a little taste of what kinds of applications that Tarleton can provide in their R&D as well as from a toolkit perspective. So without further ado, I'll kick off our session. I'll hand it to Jesse and Graham, and then finally to Troy, and we'll walk through in detail. So again, very excited and lots of content to cover today. So why are we here today? Well, if you believe Gartner, and a lot of folks do, and what they're telling us today is in the technology stack, in health insurance, in insurance in general, is this sort of combination of technology trends. And what we're starting to see now is this prevalence of analytics. We see this idea that AI and ML is really going to take it up a notch. But then we see things like NLP. We see things like, connecting multiple silos of data. And ultimately, what we're doing now is we're bringing these different sort of categories of technology, categories of process, and ultimately now this capability to do research and development in a very different way. And that's really kind of what brings us to our webinar today. These are some of the stats, and they're quite staggering. So when we look at loss, whether it's true loss or upcoding or miscoding or different categories of things, inefficiencies, et cetera, what we start to see now is that just a simple set of numbers are quite large. So for instance, if fraud is occurring, we can see in one of the statistics over here is that if you really do want to try and go to court and stop that fraud and get that money back, it's with a terrible percentage of roughly 1.7% in trying to get some of that back. And so why is this so important? Well, that's not the only element that's going on here. There are unseen costs in the human process. So more and more humans to do that. There are now compliance and state governance laws that we have to follow that really sort of add up. Each nickel and each dime and each dollar has been going up over the last 5 or 10 years. The other thing is those who are doing fraud or even loss are becoming smarter, right? They know where the loopholes are, they know where the gaps are, and then, if they are truly fraudulent, they know how to beat the system, and they're constantly changing. So what we need to do and where we need to go needs to learn. It needs to be adaptive. It needs to bolt on to what we have today so that it can enhance that. And then the next one then is really this complex network. Insurance premiums, and we'll see all those things here in a minute, are very complicated. It's not just a simple, database lookup or those kinds of things. There's an enormous amount of data, et cetera. Now we lay on our government and our compliance rules. And so now each year they change. And so there's a fairly sizable amount of just catching up from last year and then saying, oh no, it's changed again this year to go do that. And then we looked at just the simple number of human beings that you have to start to use to keep up with all this. And it starts to get bigger and bigger. And so technology, process, and different approaches are really trying to keep this sort of at bay. And again, this is table stakes that we're gonna hear today and show sort of how with Tarleton we've got a different approach. Well, let's break it down a little bit more. So when we look at our products, and we look at, ideas of claims or underwriting and the hierarchy of products in the states and who's paying us, right? Whether it's Medicare or payers or providers or what that sort of relationship is, that's a very complicated hierarchy that's fairly complex all on its own. And then you take doctors and care plans and you start to look at now what happened that was good, what happened that was bad, what happened that should have happened from a claims perspective that got billed or perhaps disputed or those kinds of things in the middle. And so now you get a very complex network of these different relationships. And ultimately, as payers and providers in insurance, you're trying to keep your patients, who are all of us, happy and trying to keep us healthy. And so then as we start to get to the back office, if you will, now we have where did the claims come from? What should the payouts be? What are the riders? What are the transaction amounts? And so when you take these three very complicated yet separate silos and then connect them, you can start to really sort of understand now why this is such an incredible problem, both from a risk and a cost, and then quite frankly, a timeliness factor in trying to get answers to those who need them. So as part of that, for those of you that are of a certain age, you'll remember David Letterman. And so what we do then is let's talk a little bit about why these sort of draw these things together. And so our first one is most of our folks that we're working with today pay first, right? They would rather sort of be in the right by doing the right thing, making patients and doctors happy. But this is an extremely expensive proposition. So in order to keep that satisfaction score high and paying early, that means that you could potentially be mispaying on a fairly large amount. And as we saw from some of those statistics empirically, it is a quite large number. The other element then is because it's hard to find why these good or bad events are occurring, it's the reason why we're paying first on number 6 above, is that it's so complex, it takes such a large amount of time and many humans are involved that it's not something that we can do in real time. But again, this is something that we want to talk about today. The other idea then of creating this time travel, so going back in time and recreating when something was paid and why should it have not been paid, or should it have been paid in a different way, just simply to find out should I have done it or was it good, is extremely complicated. So many of the systems we have today are older, and SQL style systems, et cetera, don't lend themselves to these. And thus that brings rise to some of the new technologies that we'll discuss today, such as graph, the idea of machine learning, streaming data real time, et cetera. Those are all parts of the equation, if you will. Then this risk, this act of creating a scorecard to say, is this something I should pay? Is this something that was risky? How do I categorize and even make sense of this huge heap of data is typically very difficult, and again sort of makes it even more complex in that real-time manner. And then finally, we have enormous sets of data, right? There's no shortage of data. What the 80s and 90s taught us was save the data, we'll figure it out later. Well, now's the time when unfortunately that technical debt is coming true, where we have to sort through that. We have to do it in a programmatic way or automated way. But how do we do that in the last one here, which is in real time? That's really the crux of what happens in these kinds of systems, is if you can't get even close to near time or real time, then again, you're not really making a stride forward. So again, these are all table stakes for what we're doing. So what is the risk of doing this? Well, the loss is quite large. Paying first, right, is problematic. How can we change that? How can we begin to flip that around to make a change in our organization and still yet keep our high success rate, happy with our patients and our doctors? And then ultimately, if we do this, right, it's an enormous monetary. Now, many of our payers and providers, money is not really the prime operating element, but it is always part of the equation. And it's that accuracy, it's that trustability, and it's the other elements that sort of fall as a part of this as well. That's the reason why the Tarleton alternative is such an incredible game changer. So when we look at the different use cases, there are many. It's this idea now of what is it that can be done here in the middle. And then more importantly is what feeds that, which is the machine learning and analytics that Graham and Jesse are going to talk to us about in great detail. And then ultimately putting it in human terms. That's really what this is all about, is letting humans interact with sophisticated software and solutions in a real-time manner, where they can see why things are happening. That explainable AI, as the new word has been coined. And in this case, what we see then is no one use case is a silo. Many of these are connected to each other. So whether it's in what we're talking about today is this potential for loss, right? And there are many, they still play into why do members like us? How do we cross-sell and upsell? How do we do population health management? They're all interrelated. And I think that's the core takeaway here, is that what we're going to talk about today and what Tarleton can help with may start down here in this area, but could potentially be in other areas. And the technology is certainly useful for all of those. But today we'll focus on these at the bottom. So when we talk to Jesse and Graham today, it's not the fact that your organization or your team may not have machine learning or competent AI. It's in fact the opposite. Many times, as one of our customers has said, it's a violent act of basically random acts of machine learning violence in their organization, because what happens then is they have so many individuals not writing cohesive code or creating a DevOps platform where it can all be repeatable and scalable is many times part of the problem. And so again, that's what we'll see today, is how do we take that and then how do we help your organization move it up into a more sophisticated, perhaps platform. So we'll talk more about this later, but now we start to look at what are some of these technical ingredients, right? Taking machine learning, taking a technology called graph. If you're not familiar with it, you can find it out online, but it's taking the capability of looking for patterns, looking for connected or centrality, things that look like other things, things that look good, things that look bad. And again, it's taking these raw ingredients and then let's go make a 5-star chef meal is ultimately what we want to talk about today. And these are some examples, which is these are actual examples from customers where whether it's procedure abuse or opioid prescriptions, these are the ability to increase the accuracy a fairly substantial amount, in addition to decreasing false positives are part of that. And again, Graham and Jesse are going to walk us through in more detail for what those are. But there is good news, and that's ultimately what we're all headed for. Now, as we start to look at this in a totality of a system, right, what we're going to talk about today is towards the bottom in the analytics and those kinds of things. But again, I think the capability here is with Tarleton, right, this entire stack is capable of being discussed. And this is an example of what we'll see here in a minute, which is one of those analysts can actually come in and use a dashboard, can interact visually with fairly complicated potentials of claims and what is fraud versus what is loss versus an upcode, those kinds of situations. But the goal of this is to allow a mere human to be able to come in and interact with these very sophisticated elements in a very simplistic way. The other thing then is let's look at elements that are in here and make recommendations to our human. Let's tell them that perhaps they should reject this claim or accept this claim, or they should pay this or investigate it more. It doesn't have to be much more than that, but the sophistication behind that, as we'll learn today, can sometimes be fairly complex, but we've made it very simple, and that's the real takeaway here. We can see things in different ways. We can lay things out in temporal ways. We can show it in timelines, things that are digestible to humans, where things may have happened. Has somebody spoofed my online HCA account? Has somebody done something that they should not have? Where does the linear care process, if you will? We can do those kinds of things that, again, simplifies and makes it more contextual for our human. We can see things in geospatial, right? We can lay things out in a more contextual way where perhaps they understand it in overlays, et cetera. And then ultimately, that's what we're trying to do now, is really sort of share this in a visual way. So what I'm going to do is I'm just going to show you a quick sort of overview. In this case, this is something that Tarleton uses as part of the toolkit. And then again, we'll learn sort of the magic behind the curtain, if you will, here in a minute. But when we first see this, we can change all of the data here. It's a bolt on to what may exist today. Some customers may use this, some customers may only use the research and development from Tarleton, but the goal here is that it is available. And in this case, what I can start to do then is I can see things by regions. And as we saw in our previous one, I can now say I want to look for claims that may look either flagged. So again, the system is finding things that should draw my eye. This first one I see here that this facility is in red. The other ones are in different colors. We can color treat those. We can say that there are certain categories of anomalies, perhaps, that indicate a higher risk or a red color, et cetera. And then you can see over on the right where we can start to do filtration. But as I step into this, I can now see, well, there is a location, or in this case, it's a pain clinic, and there is a series of claims that appear to be out of bounds, or there may be an anomaly here. And we can see what those are down below. And I can start to say, well, in this case, I have looked for Fran Farmington that is a mismatch. So let's dig in a little deeper. Now what I've done is I've shown the connection of this data, or its relationship, if you will. And now I can say, well, it could be the doctor, it could be the clinic, it could be the participants or the patients. It could be any of those different intersections, if you will. And as I analyze one of those, I can start to see now this layout of temporal or connected data. The system has now made recommendations that human, you should care about these connections because multiples of these claims appear to have issues, not just one claim. So now in a simple mouse click, again, I'm asking the system to say, tell me more about these. Tell me and show me what these connections are with machine learning that have made them out of bounds. And so now what I can do is I can actually preview those and suggest now that in this case, I see clusters of similar people who may also have fraudulent claims, and it could potentially be now a larger or a more advanced version of what we talked about previously, where there could be a group of people that are doing fraud to go do that. So again, this is simply a kind of a what if or art of the possible. And so we'll come back now. So with that, I'll hand it off to Jesse Crawford.
Thank you, Scott. Okay, great. So I'm going to be speaking today about a project we're doing with a major health insurance provider in the assessment of ER claims in the prepay process. And this first slide is showing the business objectives for this problem. And one thing I really want to emphasize here is everything in this list really follows if you can accomplish the first objective. So imagine that you've got this queue that's full of claims in the prepay process, and some of these queues need to be reviewed by people, and you have an optimization problem in front of you. On the one hand, if you have all of the claims reviewed by people, that's going to be prohibitively expensive in terms of labor costs. On the other hand, if you don't review any of the claims, there's going to be a lot of fraudulent claims and improper payments that you miss. So the primary objective in this study is to build a model that can accurately predict payment reduction for insurance claims before they're reviewed by a human, and then we can focus our people's efforts on those claims. Now, once you've got this first objective secured, the remaining objectives follow from that. So for example, minimizing improper payment costs follows immediately because now you're going to be able to target those high value claims and put those into the review process. You're going to increase productivity because you're going to be focusing your review efforts on high value claims instead of low value claims. Your false positive rate is going to decrease because beforehand you had this queue that was saturated full of false positives. You're going to use your predictive model to eliminate those false positives. And then as a supplement to this, as Scott mentioned, we don't just want to have a machine learning algorithm that performs as a black box. We want to have some ways of understanding that model using explainable AI and visualization tools. In particular, having a heat map of persistent financial loss gives you a way to visualize that loss and actually target it, potentially consider policy changes that may help with that. And then the last bit of this is automation is key here. We do want to embed these models into the pre-pay process so that we can identify these improper payments before the payments actually go out. So this slide is showing the economic performance of the model that we've built. Um, for all of these curves, you'll notice the x-axis shows the percentage of claims reviewed and the y-axis shows the cumulative payment reduction that's achieved from reviewing those claims. Obviously, as you go from left to right and you increase the number of claims that are reviewed, your savings are going to increase, but we need to keep in mind that this is an optimization problem because reviewing more claims costs more money. Now, in this plot, the blue curve is the baseline model that our health insurance partner is currently using, and the red curve is our model. So for example, if you can see that if 10% of the claims are reviewed, our model is increasing the savings from 15 million to 21 million. That's an improvement over baseline of about 6 million. And you can just see the other figures that are present here as you review from 10% to 50% of the claims. Now, on the next slide, we can also think about these savings in terms of percentages of total savings that are achievable. So actually that top curve that's highlighted in black there is the theoretical maximum. What that represents is if you went through the claims and you had a crystal ball that could perfectly predict the payment reduction on every single claim, that's what that curve actually represents. And so for example, you can see that when 50% of the claims are reviewed, the theoretical maximum savings is 98% of total. Our model is achieving 94%, and then the baseline was only 83%. So again, you can see that there is a significant savings achieved using these models, and this is really promising. So the question is, how is this achieved? So on the next slide here, this shows a artificial neural network, and this is basically the state of the art in machine learning right now is deep learning. The way these models work is you take the input data, all of the covariate data for claims, those are going to enter into the network on the left-hand side into those input nodes. And then that data propagates from left to right through the neural network until it arrives at that far node on the right-hand side, which gives you a predicted payment reduction. Those predicted payment reductions are compared to the actual payment reductions in your training set. Errors are computed from that, and then those errors are propagated back from right to left in an algorithm called the backward propagation algorithm, and that's used to optimize all of the weights of the edges in this neural network to optimize the performance. So to make a long story short, we use the forward back propagation algorithm to optimize these neural networks, and the software that we use for that is PyTorch and TensorFlow. And so then our next model that we've been using is random forests. This model basically works by building an ensemble of decision trees. So you can take a data set, you can fit one of these decision trees to the data set, which is essentially like a flowchart structure that takes the data and successively breaks it down into finer and finer subsets where the predictions become more and more accurate as you go down the tree. You build a large number of these trees, like in this figure, there's 600 trees, but you can easily build thousands of these, 2,000 if you want to. And then you take an ensemble of all of these predictions and aggregate those into a single prediction. And this is a highly competitive method as well for building machine learning algorithms. One nice theorem by Bremen here is that random forests are actually robust against overfitting. And so this can be a really nice model to deploy in the early stages of a problem where you just want to get like a rough idea of how the model should work. And you want to avoid overfitting early on in the process. So thankfully, we have this nice little theorem by Bremen that shows that these are robust against overfitting. So as mentioned earlier, we don't just want to look at these machine learning algorithms as a black box. We want to think about explainability. This is another nice advantage of random forests is they automatically provide us with variable importance plots that show how each one of these variables contributes to the accuracy of the model. So, this slide's a bit hard to look at. This is the sort of raw data from the random forest. Let's go to the next one. This next slide will show more of an outline that kind of clusters these variables into different categories that shows the relevant aspects for predicting payment reduction on ER claims. And there's really 4 broad areas. The first area has to do with reimbursement method. These are the most predictive variables in our model. And what this really gets into is the idea that someone committing fraud really likes to take advantage of financial carve-outs and contracts that allow them to bill services as a percentage of a charge rather than as a per diem flat rate. So if you have services that are subject to these kind of carve-outs, this is a financial exposure that allows someone committing fraud to come in and optimize the profitability of their fraud. So that if you see an entity that is engaged in billing these financial carve-outs at a high rate, that could be an indicator of fraud. The next category are churn metrics. These are both on the provider doctor side and also on the consumer patient side. Doctors that are seeing inordinately large numbers of patients, billing excessive numbers of observational units, or unnecessarily unbundling visits into large numbers of claims. These are indicators of fraud. Patients that have a tendency to visit a large number of different doctors may be engaged in doctor shopping, often with the specific goal of getting prescription drug abuse scripts, like as we can see in the third category. Unsurprisingly, prescription drug features are another statistically significant predictor of payment reduction and fraud on these claims. And unsurprisingly, opioids is the top one here. We're grouping these prescription drugs by the generic product identifier code, and we see things like opioids, anti-anxiety, and antidepressants as being the top 3 predictors in this area. So the last part, we start to get into a sort of high dimensional space of predictors in these models. And that includes things like diagnosis codes, revenue codes, and HCPCS codes. And HCPCS codes, you can almost regard those as basically additional features of diagnosis and revenue codes. And when I say high dimensional, I mean, for example, that for diagnosis codes, there are 1,900 different codes to consider in the model. And if we leave a variable like this at this high degree of granularity, that can cause instability in model estimates and low model performance. So if we can go to the next slide here, this is going to show a technique that we use called hierarchical agglomerative clustering. And you can't really see this very well, but at the bottom of this plot, all 1,900 of those diagnosis codes are represented in that very dense black region at the bottom of the plot. What we do with those codes is we use metrics to embed those into a metric space where we can calculate the distance between any 2 adjacent codes. And those distances are then used to create this hierarchical tree structure that you see in front of you. And then what we can start doing on the next slide is we can start cutting this hierarchy at various heights, and we can just keep going and cutting it in different positions. Every position that you cut it in defines a different clustering. So the first cut that we had at the top, where it only cut the tree in 2 positions, would result in a clustering of size 2. And then as we move down, we get different numbers of clusters. This is really an optimization problem. Again, if you have too many clusters, you're going to have model instability. You're going to have high standard error model estimates. And if you have too few clusters, like we saw at the top with only 2 clusters, you may be underfitting your data and you may get poor model performance in that case. So actually on the next bit here, we have a clustering optimization plot. And really this shows how we can evaluate the quality of a clustering. We basically look at every single possible clustering on the x-axis and we model its performance on the y-axis using some type of performance metric like ordinal AUC is the example here. And so in this case, it looks like the optimum is, you could say it's occurring around 40 clusters. There are actually considerations in this model that recommended scaling it back to about 10 clusters. And we can show the performance on the next slide for that. We actually see on the following slide a setup where we have grouped those diagnosis codes. So just as a quick reminder, we started off with 1,900 diagnosis codes, and trying to feed that into the model will result in model instability. We've trimmed that down to 10 diagnosis code clusters. And this has 2 benefits really. One of the benefits is that this improves model performance, but also there's sort of an ancillary benefit that you've automatically clustered your diagnosis codes into risk categories. And you can see very easily right here that something in diagnosis code 10, that would be something like a heart attack or a broken leg or something like that. That's going to have a higher severity level associated with it than something in risk category 1. That's probably something like, a cold or something along those lines. And then you can use this data to assess, is there a tendency at a given hospital for the providers at that hospital to take low risk categories, but still assign high severity to them. If you see something like that in your data, that could be an indication of fraud. And then just on the next slide, we have another plot, which is the same for provider financial keys. Provider financial keys are the unique identifiers we use to keep track of different entities like hospitals, emergency rooms, healthcare providers. And we can basically do a similar thing here where instead of trying to look at thousands of different provider financial keys, we can assign them into risk categories. And we see a very strong relationship here between provider financial key cluster and payment reduction. You can start to identify entities that have a higher chance of having a claim that results in a payment reduction. So that's one side of explainable AI. One side of it is kind of identifying variables that contribute significantly to the model and just focusing your efforts on understanding what's going on with those variables. But then the next part of this is going to be the visualization component. And the way that we're thinking about this is the target variable in this entire study is predicted payment reduction. That is represented as a heat map with a color gradient in this plot. And so points that are dense in red points, those are going to be the points that have a high probability of payment reduction. And then green and yellow is a lower probability. The plot that we're looking at here, on the x-axis we have build amount, and on the y-axis we have financial carve-out. So that was something mentioned earlier today, is contracts where there's certain billing arrangements set up so that someone can bill as a percentage of a cost or using a financial carve-out. We had reason to believe earlier in our analysis that financial carve-outs might be associated with higher rates of payment reduction, and we're definitely seeing that in this plot. As you see, as you go up from the bottom of the plot to the top, and we have higher values of financial carve-outs, those are associated with a very dense cluster of red points, and those are going to be the points that give us a high expected value of payment reduction. Then, as Scott mentioned earlier, we can take these plots, we can click on one of these, drag it over to the right-hand side of the screen, and we create an entity node relationship diagram. The plot, the node in green here is a claim, and we can expand that claim out from that, and we can see all of the entities. The ID numbers are hidden in this demo, but you can basically see the ID number of every patient and every provider associated with that claim. And in fact, that lower node there is a hospital. So then we can click on that hospital, expand that node out, and then that's going to show us all of the other claims and other providers that are related to that hospital. So basically, in summary here, our approach is identify a target variable that will maximize the economic performance of the organization that we're working with. We want to use machine learning to build predictive models for that variable. And then we want to be able to create other types of metrics and visualizations that allow us to understand that model, make sense of the output that we're getting, and maybe even consider, different directions that the organization should move in. So that's my time. I'll turn it over to Graham.
Thanks, Jesse. And so thanks, Scott, for teeing up the discussion today. And then thanks, Jesse, for showcasing how the technology works. I'm going to try to bridge the gap between those two things by talking about how we get that technology into the hands of our users, who in this case be claims investigators. What we're looking at on this slide is two different pieces of the deployment puzzle, and that is training the system, as Jesse was just discussing, and then getting the system out the door into core product. So those are two distinct pipelines. And Scott, you can just click through those animations there so we can see all of the characteristics. During training, we go through a bunch of experimental processes, including feature engineering and model design. And when we've arrived at something that gives us the best payment reduction predictions as measured historically, we then deploy that model into our inference pipeline. And we do it using the following technologies. On the next slide, what we're showing here, is the technology suite that we use commonly to deploy, both train and deploy, in fact, our models into core product. And as you can see all the way on the right-hand side there, this slide is built generally just to note that you can deploy this onto a variety of different architectures. So if we have mobile devices that our users are interfacing with, or desktop, and then, of course, in other use cases, they go into other types of hardware. The important note to consider here is that as we move through processing, training, and deployment, the entire time this system is recursive in that it ingests signals back from our claims investigators based on whether or not the recommendations we're providing are realistic or not. Over time, what that means is the system improves in accuracy. And on the next slide, what we have is a view of the technologies we use in our full stack to enable that system. Now, what we're looking at here is a combination of cloud-based tools and on-prem tools. Of course, we've done this many, many times and have worked in every cloud provider. And if you have questions on individual deployment characteristics, like I want to make this system work on AWS, just reach out. We can show you some reference architectures we've used in the past. Suffice it to say that the front end sits all the way at the top of this diagram, and that's what Jesse was just showing. And the data comes in at the bottom. In the middle there is the analytics, the machine learning that Jesse was just discussing. And the recursive nature of the system is the thing that I want to touch on here, which is intimately tied with the deployment scenario and is really important to our users to be able to give us information back on whether or not the system is useful and in which places it's not useful so that we can update it. The way that that works is by using a system that looks like this. On the top there, we have data coming in from a variety of databases. Could be streams, like something like a Kafka stream, or, and what we always recommend, is that some of this data comes in from a graph database. And when we have all of those sources of information, we can use different characteristics and different detection methodologies to combine into one overall recommendation on payment reduction prediction. That is the combination of machine learning methods that Jesse just shared. And it is definitely a combination of the business logic you already have in-house. For instance, any claim over $2 million automatically goes through review. And we can use graph-based detection methodologies in concert with those first two systems. We use a compositing system, which combines that information, those recommendations. And then that feeds into a UI, which we'll show shortly, which ensures that the users have the opportunity not only to let us know if the system was making accurate characterizations, but also to interrogate the system as to why it was making those decisions. And that's the explainable AI characteristics that Jesse was mentioning earlier. So let me jump into an example. Let me show you what this really looks like. This is, and of course we can't show the individual payment reductions estimated here. So I've just had the reject or approve threshold on the recommendations column. But what we're showing is the system that the actual analysts interact with, so they can see the claim characteristics. They can see, of course, all this data is synthetic. They can see the amounts of the claim, and they can see all of the information that's related to that claim and how the system recommends whether the claim should be used under investigation or should just pass through without investigation. And the interesting aspect of this system here is that as we dig in, as our claims analyst digs in, on the next slide, we drill into one of these claims. We can see the characteristics of the actual individual line items that affect that claim, geospatially, and of course temporally too, if that's important. And we can showcase to that user where and why those recommendations were made. And we show that through a variety of methodologies. The one, of course, that we're showing here is just based on feature importances, which Jesse spoke about as well. One level deeper, using the graph-based system now, is we can look across similar and dissimilar claims to understand whether or not this individual claim is related to other claims in our claims database. And that's critically important because, as we're all keenly aware, some of these claims, when there are anomalies or when there are potential fraudulent behaviors on the claims are related to other claims. Now that might be through a provider, that might be through an individual consumer, might be through some service-based network, something like that. And we use the connections in that graph database to be able to, as Jesse showed earlier, ferret out the commonalities between those anomalous claims to understand what that expected payment reduction will really look like. So to summarize the human in the loop feedback mechanism here, we have a very simple UI that allows a user to do one or two or zero things, all of which are important feedback for the system. One is the user could just simply say, no, I don't like that decision. Or they could say, yep, that looks right to me. The other thing they can do is they can actually provide some explanatory reasoning about why they don't trust or why they do trust the recommendation that's provided by the system. When they do that, they're actually helping update that system. And this happens in real time. So what we do is we feed that information back into our feature database, and we use those updates to retrain a model, retrain the model in a consistent way that ensures that in future and subsequent recommendations, the accuracy is higher and higher on average over time. And it looks like this in cartoon form. On the top right, we have a fraudulent claim detected by our system. We populate that information into the UI you just saw, and the user can choose one of three paths. One is just ignore it, just do nothing, and that's just fine. The other is they could say, no, that doesn't really look right to me. Or the third is, that doesn't really look right to me, and here's why. And in that case, the reasoning is the build amount is under the threshold. This is a negligible amount of money, and we need to move on and spend time on more important and valuable claims to our business. In both of those cases, what we see is a pipeline that injects information back into that model in real time and fully automated, by the way, to be able to update that model and in the future serve better recommendations to the front end. So 4 things underlying this entire system here. The first is you have to have monitoring in place. You have to understand how your data is changing over time and how your model outputs are changing over time. And we do that again using the power of graph and the power of online data. The second is we have to be able to do something about it in real time or near real time. There are a suite of technologies that enable that machine learning CI/CD pipeline. If you want to learn more about that or any of this stuff, click that, visit that link on the bottom of the slide. The third is the actual updates of the system, and that's the human in the loop feedback that enables that autonomous update for improvement of accuracy. And the fourth is the interpretability metrics that we looked at, our claims center analysts looked at to be able to understand why the system made the recommendations it did. So that's it for me. Thanks. I'm going to turn it over to Troy.
Thank you, Graham, and thanks everyone for participating in today's webinar. Again, my name is Troy Thorne. I am the director of the Tarleton Analytics Institute at Tarleton State University, as well as the Center for Agribusiness Excellence here at Tarleton State University. Just so you know, Tarleton has been a leader in advanced analytics for over 20 years. Back in 2000, Tarleton created the Center for Agribusiness Excellence in partnership with the U.S. Department of Agriculture to provide advanced analytics and data mining in support of the federal crop insurance program. Over the last 20 years, the OMB has given us a return of about $1.5 billion, which amounts to about a 23-to-1 return on investment on the part of the federal government. We are identified as one of the most successful governmental analytics programs. A few years ago, in order to expand our footprint and be able to provide analytics to other partners, Tarleton created the Tarleton Analytics Institute. At that time, we began to partner with the math department as well as other departments on campus. Our model pairs research partners, which is what we call our business partners, with faculty mentors and undergraduate and graduate students. We believe that it is imperative that we create this partnership that includes students at all times. One of the things that we determined or we identified over the last 20 years is that when we hire a new person at CAE as a data scientist, they come in and there is a long learning curve because the data sets that we use and the rules of program participation associated with the federal crop insurance program are so complex that it takes a considerable amount of time in order for that person to gain what we call domain knowledge. Once they have domain knowledge, then they become a productive employee and we can actually assign them specific projects that they can then do on their own. However, until they have acquired that domain knowledge and understanding of the data sets and understanding of the program participation rules, it really takes their mentor along with them in order to produce a product that we feel comfortable with. Identifying that, we decided that it would be of great benefit to our research partners if we were to include graduate and undergraduate students so that during the course of the project that we are partnered with, these students get that applied learning. They acquire that domain knowledge. And so what we hope to achieve is a win-win, where not only do we create an analytic tool for our research partner, but we also can create a portal of employees through Tarleton State University's graduate and undergraduate programs with students who can then go directly into employment with domain knowledge and become a valuable asset from day one. This is part of the mission and vision of the Tarleton Analytics Institute. I also want to make sure that those of you who are listening in today understand that although we have primarily talked about, or at least Graham and Jesse primarily talked about what we've done within the insurance industry, we believe that we can provide risk mitigation services for all companies. There are just some parameters that have to be met. First, obviously, there needs to be a specific business question that needs to be answered, problems that need to be addressed. I'm sure that everyone who is tuning in today already knows what types of questions, or if not the specific questions, they would like to be able to answer using their data. Second, we have to have adequate data, which includes historical as well as current data. Typically, when we start with a new partner, we like to run what we call an red, amber, green test against the data sets that they're able to provide for us. Knowing exactly, or at least a good idea of exactly what data we need, we can run through the data set, identify as green all of those that are readily available and ready to ingest, identify as amber all of the columns of data that appear in some fashion that either in part meets the requirements that we need, or will need a little additional information or additional ETL processes in order to move it over to the green. And then we identify the red columns, and those are columns that don't exist. Those are things that we need in order to provide the best analytic services. Those in the red, we realize are going to be more difficult to acquire, and we start to look for ways around that or ways to identify how to get that data. Now, as you can imagine, Once you apply the red, amber, green test, then you have a pretty good idea of the level of effort associated with the project itself. As many of you know, the ETL process is 80% of almost any analytics project. And also, we want everyone out there to understand that although we have a considerable amount of domain knowledge in many industries, we don't have it all. And so with our partner, what we like to do is we like to identify a person within our partner's employee who we consider to be a subject matter expert, who we can then walk through the data with them, walk through the business questions associated with the project, walk through the rules of program participation, and utilize his domain knowledge in order to help us to develop and hone our models. That's a part of our partnership model. Next, let's talk a little bit about levels of engagement. We talked about the red, amber, green chart. Now, the ETL process itself, as I have stated, is a large portion of the analytics project. As such, it typically identifies to us, along with what the expected outcome is, what the initial cost of the model development is going to be. But straight model development is our lowest level of engagement. This is simply where we come in, we do the ETL process, we take a look at your data, we create a model that answers some business question, and then we provide that analysis back to you for vetting. And if it meets the requirements, identifies the answers that you're looking for, identifies a cost avoidance, whatever the case may be, then we present that model to you to utilize within however you see fit. This is the lowest level of engagement. The next level of engagement would be model development with enhancements and maintenance. And the reason I identified this particular one is because once that model is developed, it is only good as long as the parameters do not change. And the parameters can include program participation, it can include additional data, it can include the rules associated with requirements associated with the program participation. Anyway, if anything changes that is utilized as a parameter within the model, then that model is going to have maintenance in order for it to continue to provide accurate results. And so the second level of engagement is the one that we typically see minimally with partners, and that's model development with enhancements and maintenance. A lot of times once the model's developed, we can give it back to the company partner. They can let their subject matter experts look at it. Then they maybe want some enhancements, some engineered features, and then we can do that. Obviously that comes with additional costs. The third level of engagement is model development with visualization tools. We utilize a number of different visualization tools. We have some that are in-house that we develop. We have some that we develop with our partner Expero. We also have situations where we use COTS visualization tool, Tableau, for instance, that resides right on top of the data set that we create or create during the ETL process. A lot of times the visualization tools really are able to put a red spot on the bullseye for folks. We also can develop the visualization tools at all levels of participation within the project. In other words, we can develop more granular visualization tools for, say, analysts, and more 3,000 foot level visualization tools for your executives. And finally, the last is end-to-end analytics. This is what we do for the federal government. This is where we ingest the data, we do the ETL process, we do the analytics, we create the visualization tools for not only the tabular but the visual data as well. And then we act as a repository for their not only their analytic results but their inspection results as well. Going a little bit more into that end-to-end analytics, I already identified that within that project or within that process, we would do the data ingest, the ETL, the analysis, the visualization tools, tabular and graphical. And then we act as the repository for not only the analysis, but also the inspection results, as I alluded to. And I apologize for reiterating that, but that is an option. With that option, we tend to require a lot more access, if you will, to your systems, etc. Another way that we can provide the data back to you or the analysis back to you is through an external application. We do this with some of our partners already. This is where we have a partner system. They send us the data. We then create an application that resides outside of the partner system that they can access via some single sign-on, whatever type of security is required. We do the analysis with the data they send us, and then we return the analysis either to the partner site or to the cloud, wherever the data may reside or the application resides. But this is external from the partner system, external from Tarleton Analytics Institute system. And so this is really the, there is less access by our folks to the partner systems this way. The next way is an internal application. I personally feel like that this is the best scenario. This is where we create an application and a model that resides within the partner's platform as part of the internal workflow. So as you ingest your data at whatever point during the adjudication process you feel it necessary, we then install the application within that workflow at that point where it can read the data as it comes through and do the analysis in real time. If we are going to do prepayment analysis, we believe that this is really the only way that becomes possible. Why partner with Tarleton Analytics Institute and Galaxy? Well, as I stated, we do have a long history, Tarleton does, of analytics. We have a great record of reducing improper payment rates. Right now, with our partnership with the federal government, we have RMA's improper payment rate down to approximately 2%. That is 400 times better than any of his peers. We pride ourselves on going the extra mile in our analytics to make sure that we reduce false negatives and positives. We automate our anomaly detection and we look for the deep links. We can talk more about that some other time. Our goal is to stop payments and avoid clawbacks. Clawbacks is a term that we use that identifies when an erroneous payment has been made to a producer, to a provider, to whomever it might be, and then the industry or the partner has to go back and then identify that the payment was made erroneously and they have to ask for payment back. We want to stop payments prior to. We talked about bolt-on leveraging the current platforms. We realize that most businesses have a considerable investment already in IT platforms, and we want to create a scenario where we bolt on our application, whether it be in the workflow or outside of the system itself, so that you can leverage your current platform. And finally, we have a long history of risk mitigation through advanced analytics. Thank you for hearing me today, and I will open it up for questions.
Super. Thank you, Troy, Jesse, Graham. Great information today. And I think the core takeaway here is at the bottom here, go ahead and start typing in your questions, is that it sounds like, Troy, it's flexible and then it really can bolt on. You want to talk a little bit maybe about sort of how you can sort of leverage what they already have?
Absolutely. Most organizations already have a significant investment in their IT infrastructure. What we don't want to do is we don't want to come in and just say, okay, you're going to have to scrap this entire platform that you've done or that you've created over the past 6 years that you've invested, this dollar amount in, so that we can then input our platform. The way we create our applications is they're flexible. They can bolt on to almost any existing system, and then they can be tailored to ingest the data and export the results to your particular company's needs. And so it's very flexible in that regard.
Okay, we got our first question here, and maybe this is to you, Jesse and Graham. Is it says that if we wanted to get started, is there a data minimum size that we would need to provide that could start to give any sort of results?
Interesting question. I think the answer effectively is no, as long as the data you have on average describes the space you want to operate in. And the example there is if you have claims which which are dependent on ERs, freestanding ERs, for instance, you'll want to have some historical data about that. If you want to analyze claims that are mostly related to prescription-based fraud, for instance, then you'll want to have some data that historically represents that as well.
But it doesn't sound like there's some minimum.
No, usually what we do is we have methods to supplement data if there is very, very limited amount. Typically, though, we really need not that much data to build a model which really has pretty high performance.
Okay, it looks like we got another question here. This one's for you, Jesse, which says, we have 15 to 20 machine learning team members today. Would your team plug in and work interactively, or would you work separately?
We're happy to work interactively. We are currently in a relationship with a major insurance provider where we meet with them at least bi-weekly, and we usually meet every week. So we have a set time set aside, and we basically collaborate with each other in terms of both model design and deployment. And so, yeah, we're really happy to work as much as our partners want to. If we have a partner that prefers to be kind of hands-off and give us something to work on, then we're happy to do that. But also, if we want someone to be really involved and integrated, then we're very excited to have those kind of partnerships.
Fantastic.
I would add one thing, Scott.
Sure, go ahead.
Real quickly, and as Jesse alluded to, we're extremely happy to work interactively. We feel like that's the most productive. In the event that there are partners out there who A, do not have a data science team, or B, simply want to do a one-off that is separate from what their current team is working on, we're happy to do that. We do not assume to have all of the domain knowledge for every industry. So even at that, we would have to have interaction with the folks back at that particular partnership to ensure that we understood the program rules, the rules of participation, how the data is structured, et cetera.
Okay, super. Well, that brings us to our time today. Thanks again to everybody for attending. And again, this is being recorded, so we'll post that out online. So if you have other friends or practitioners or people who might be interested, certainly pass it along. And thank you to Galaxy for hosting. And that's it. Everybody have a great day.
Thank you.